What's up, hackers? Welcome to Chill Code. And tonight we are taking a look at offensive Nim, which we've played a little bit already with on the stream. Did a lot with Husky last week. And we're going to be comparing it to offensive Rust. Now, some of you know, look at that cute little guy with the demonic horns. A lot of you have expressed some shall I say, displeasure with the Rust programming language because its syntax is, well, it's not Python. uh, that being said, I really like Rust. I think that it's an important language. I think that what Mozilla is trying to do, actually, no, I misspoke. It used to be a project under the Mozilla Foundation, but since that time, um, Rust has separated and it is its own nonprofit now. But I really respect what they're doing from a systems programming standpoint. They're trying to create a safe and secure replacement for C and C++. I think that matters for systems programming. And yes, the syntax is going to be a little bit funky because of the way that they're doing what they're doing. That's a little unavoidable. Nevertheless, once you get over that initial hurdle, I find it a really pleasing language to work in. And the tooling around it, especially for a systems language, very low level, is really, really, I think, modern feeling. So, with that in mind, we're going to take a look at the differences between these two repositories. And big shout out to Trickster0 and, of course, Bytebleeder or Marcello Savati for putting these two together. So, we've linked up the offensive Nim repo before, but let's go ahead and put that in the chat as well. And here's offensive Rust if you want to play along. Now, if you've never set up Rust, we've gone over how to set up Nim on the stream before, but if you've never set up Rust before and you want to play with Rust in this way, what you might want to do is go to rustup.rs. And this will walk you through installation of the Rust toolchain on either Windows or Linux or Mac OS. And it'll kind of just, it's designed to be run, you know, you've got Rust up init, or if you want to do it in WSL, they have that there for you. It is detecting my operating system. That's why it's giving me both of these. Once you have that, you'll have cargo for Rust, and then of course Nim we've set up before. So the Rust tooling is a little bit heavier duty, so we'll talk a little bit about how to make this work. But the plan is we're going to test both of these, see what the different payloads look like, and see what kind of detections we can get going, or not, in fact. So I also have my Flare VM machine up and running. We're going to use that as kind of our test bed. I've got Windows Defender set up here, ready to go, and we'll see what it can do for us. So let's start with a quick tour of the two languages. So let's take a look at the offensive Nim, which we've done before, and certainly we've written our own versions of some things before. But let's take a look at something we're familiar with, which is the shellcode inline. Nope, wrong one. Which one do we want? We want shellcode bin. That's it. This is the one that we're used to working with, right? This is what we based our own obfuscated version of this on. So we are importing two libraries, WinIm, which is the Windows API, and we're importing OSProc, fair enough. And then we have this function or procedure in Nim called inject create remote thread. And this is where we create the remote thread, we inject our shellcode into it, and then we listen for whatever happens after, right? Here, this is MSF Venom, just a message box as a demo. But of course, we created our own shellcode and played with that as well. So all told, with spaces and comments and things, we're looking at 116 lines of code. It's fairly readable, except for the bytes part, but that's not supposed to be readable. Now, for comparison, let's take a look at the same thing in the offensive Rust repo. So the first thing I need to do is I need to get to the shellcode local inject. Potentially no, I want to go to the process injection. So first of all, you'll notice that even the structure of the directories is a little bit heavier duty in the Rust side, because each one is a full-out cargo project. Each one is the cargo toml. So, and these two dependencies are really, really important here for what we're doing. The WinAPI crate is the language for Rust, and the kernel 32 sys crate. And we'll take a look at the documentation for that in a minute because I think it's interesting to see how Rust does its documentation. But then the target, does it already have a build in here? Hilarious. It looks like it might. This stuff shouldn't be included in a Git repo, just as a heads up. You should be setting up git ignore to ignore your target because that's like the build location. But okay, so here's our main.rs, and let's take a look at what we're dealing with here. I'm gonna make this a little bit bigger, just because this looks like a slightly wider window. Okay, so in Rust, we're using the kernel32 crate. That's kind of like an import. And the imports in Rust take two steps. The first is you declare that you're using an external dependency, and then inside we're going to use kernel32 and we're going to, oh no, that's it. And then use WinAPI. And here we're using WinAPI, WinNT. And these are constants that are set. All of these have different integer meanings, I believe. But they're flags that we're passing to our function calls so that the WinAPI knows what to do with them. So the first thing we have, this could be commented a little bit better, but basically, is this byte for byte the same? No. So I don't know what the shellcode is, and we might want to test it with our own. But, so we're creating a byte array. Remember, bytes are just 8-bit integers, so that's why we're declared here, test, and then this is actually a slice, not an array, but same diff in Rust. But it's an unsigned 8-bit integer, and then it's 276 elements long, and so there's our slice. And then look how short this code is. I mean, it's verbose this way horizontally, but not vertically. And then in unsafe, what are we doing? We're saying we're creating a mutable variable. That's what mute does. By default in Rust, every variable you declare is immutable. You have to specifically declare it's mutable with the mute keyword. So H is going to be a handle, presumably. And that's the kernel32. We are opening a process, whatever the process is. And this has to be open process. Is this? We might want to check out the kernel32 documentation for this, because what I feel like is missing here is the process ID, which might be here. I think this to me looks like the process ID because we're not seeing that number 31736 anywhere else. This might have been just hard coded into the repository, so we might have to do some work there to clean that up. And then let mute adder equals kernel32. We're allocating the virtual memory, creating a null mutable pointer. We're sending it in our process handle. So that's the first place we do it. There should be spaces between these arguments. And then the shellcode length as a unsigned 64-bit integer. This is how we do sum typecasting in Rust, where if you have an 8-bit integer and you need to turn it into a 64-bit, you use the as keyword, and Rust will handle the conversion for you. That's one of those things that, in Nim, you don't really deal with that much because you just have a straight up int most of the time. Whereas in Rust, you do have to care about how many bits your integer is actually taking up. And then we have some flags here. Mem commit. And then mem reserve. Page execute. Read write. Okay. So we're setting up our properties for our new memory space, right? We're making it execute and read write. So we're giving ourselves the ability to execute the shellcode here. And then we create an n equals 0. Right. This is going to hold how many bytes have been written. I believe. And then and here we perform the write, kernel 32 write process memory. We're writing into our handle the address that we've gotten for our virtual memory allocation. We are using our test shellcode as a pointer. So wherever this thing was in memory, we're actually sending it there. And then as nothing. And then how many bytes are we writing? We're writing test.length as u64. And then the buffer to count bytes written is going to be a reference to our n counter here. That's what the ampersand says here. And again, mute because it's mutable. Okay. And then the thread is create remote thread, do the same thing, null mute. And then this gets a little bit harder to read here. And then kernel 32 close handle. Okay. So, I mean, the same process that we're used to with a create remote thread kind of injection. But there are some differences, like how this thing is actually put together. And the shellcode that we're using, of course. And in particular, the kernel 32 API, which is a little bit different in how it's getting called. I mean, not super different, but if we look at the Nim version, create remote thread, there's our, let's see if we can do a side-by-side here. So on the left, we have the Nim, whereas our handle, there's null. Very, very similar in terms of, I mean, it has to be the exact same arguments, right? It's the same API call from Win32. But the way that it looks in Rust is a little bit kind of more verbose because of the way that we handle types and things like that in Rust. Nevertheless, all things considered, not that tricky. Now, I'm going to try compiling this Rust and see what happens. I expect to get a Defender alert on my system right away. And in fact, I think I have cargo set up in Kali. Let me confirm that. So many programming languages in so many different places. Let's shut down the web stuff we were doing last night. Cargo. Yep. In fact, I'm going to run Rust up update to get the latest version of Rust. Cool. So the reason I'm doing that is so that I can compile this stuff in Kali if I need to. In my offensive Rust folder here, I'm going to cd process injection create thread. And then I'm just going to do I have Ming 30. I have everything I should need. But let's get the right shellcode. You know what I mean? So we're going to get the right shellcode out of here. We'll make Rustterpreter as our and MSF Venom. So let me just check to make sure that my IP addresses are good. Yep, still good. So we're going to MSF Venom. Very, very similar to what we did before. And let's actually look at the way that bytes are written in the Rust source. So pretty much identical to how things are looking in Nim. So we can do the C# target for Meterpreter and use that as our base. Same deal. So we'll pretty much do exactly what we did before here, except I'll rename it to Rustterpreter. Okay. And then so that's 200,262 bytes. Sure enough, I'm gonna grab all this. You know, it's easier to just go to the bottom. There we go. And I've yanked this in Vim. Now, if my clipboard is set up correctly, this should work out. Woo! Look at that. Very stupid amount of shellcode. And what we surmise is that one of the reasons why this keeps evading detection is because it's so dang big. And in fact, we'll do the same thing over in the Nim build as well. Okay. And all right, there's Rust done. That should be like that. Oh, don't need that extraneous. Okay. Now the trick here, I always forget how to do this because I don't have to do it that often, but there is a way to compile the windows. Yeah. That's it. I have to add, I think I've already done this, but just in case, there's some stuff I have to add to the target to Rust to make this work. Yeah, there we go. Pretty much just like that. It's not that much harder, honestly. We're installing the toolchain for stable x86-64 Windows stuff. Can you share, please, the command? Okay, I'm looking to set up Linux to compile the Windows. The first thing you're gonna need to do is right there, and then right there. But you should also know how to look that up. I'm just gonna call that out. That I'm happy to share commands and things like that, but that was a one step for me to go find, and something that you want to get in the habit of being able to do. So we're going to cargo build and with the target x86-64 PC Windows GNU. And the GNU just means that we're going to use the GNU builder rather than the Visual C++ builder, which is what Rust C uses if you build on Windows. It uses the C++ runtime, the C++ compiler. So while that's building, because it might take a second, let's go to crates.io, which is the package catalog for Rust, and let's look up kernel 32 sys. So this is it, and let's go to the documentation for it. Or, you know, not. Documentation. Okay, so here's WinAPI. Oh, annoying. Weirdly, so user mode headers. This is the stuff that we saw in the top of our source before, right? Where user mode winNT. So if we go to user mode, we go down to winNT. Here come all the structs that we saw before. And if we inspect these any further, let's take a look at process all access, for example. Processor, process mitigation, process all access. Is there a struct one below that I missed? winNT. Nope. There it is. It's not alphabetical for some reason. But yeah, look, you can see what it is. It's a D word, and these are the C types that basically the WinAPI package is creating compatibility for us for, right? Standards required, or synchronize, or 0xFFF. So it's trying to use these other consts, and if it can't, then fail back to this. So there you go. That's how the WinAPI library here is working. Now the kernel 32 library is not the WinAPI library, though, right? And I'm concerned okay. The documentation seems to be like not present, which is concerning. And this is, I think, the hurdle I ran into when I tried to build these exact projects. So what Trickster Zero must have done is kind of just intuited and used Rust Analyzer or whatever to figure out what the API calls were going to be, even though they didn't have the documentation available. Okay, by the way, this thing built, it's like on my file system, and Windows Defender doesn't care. Worth noting. This did finish. So if I go to Target and I go to x86 Windows GNU and I go to debug, you'll see that I have process injection create thread.exe. And I'm going to CP that exe to Rustterpreter. And then I'm going to move Rustterpreter. It's currently in the Windows subsystem for Linux file system. So I'm going to see what happens when I move it over to my downloads folder. Yeah, Windows Defender is on, and nothing is happening. Oh, except interestingly, I didn't get an alert, but oh, it is flagging. It's just not giving me a it's not giving me a notification. It is flagging. So the default here is flagging as Meterpreter. So that's good news from a defender standpoint. Not such a good bit of information from the defensive standpoint. But interesting to note, by the way, that it didn't work like how can I say this? It's resident as process injection create thread in WSL, but Defender can't see it because it's in WSL. And interestingly, because of the way the WSL works, I can actually fire off executables from WSL. Like I could fire this off, and if I had a listener that was waiting to do it, like it would work. So the trick now is that I just need to zip up this thing and get it over to my lab machine to see what happens. So I'm going to... All right, so we'll zip that up, and then we'll cp rustinterpreter.zip over to WinHome and download so I can get easy access to it. And that's sticking around for long enough for me to do something with it. So let's go ahead. Oh, there's a Husky's cat still in our lab machine. And in fact, what I should be doing, in fact, I will, is I'm going to revert to a checkpoint. Yes. So we'll go back in time to make sure this is a clean test. How's everybody doing tonight? Hey, Orbital. Okay. Oh, interestingly, the last the last checkpoint still had Cosmo on it. That's okay though. So we're gonna go to downloads here, and gonna knock off all this stuff because I don't need it right now, and paste in rustinterpreter, and then we're gonna extract it. Okay, let's go back over to Kali and make sure that we have our listener set up. Okay. Now again, I expect this thing to get caught, but nevertheless, we'll set it up for listening anyway. Okay, so a couple things to call out. I don't know if you remember how large the Nim version of this was, but it wasn't 14 megs. So one of the things about Rust binaries is that they tend to be a little bit heavier, and here we're definitely seeing that. If I have, let me see if I can go over to Nim here. There's the Nim reverse shell. There's the CS. I don't have the actual thing, but whatever. It's tinier by a good bit. I thought it was like 400 kilobytes if I remember correctly. Oh no, I have it right here. Nim interpreter is 676 kilobytes with even the big interpreter payload in it. So now, why is this not getting caught, whereas it did get caught on my host system? That could be because the Flare machine needs some updates and it hasn't been on the internet for a few days. That could be part of it. It might be a newer detection, right? The Microsoft Threat Intelligence Center folks are watching the same sorts of things that we are. So if they saw that this new repository came out, they would do the same things we're doing and build detections for them. So this might not have those yet. That might be why. But let's see if this fires up and works as intended. Let's get our Metasploit console over here. And so no, it did not. Oh, wait. Of course it wouldn't. Because we forgot a part. And this is one of the things that I think was a real problem with the Rust source code. In fact, what I'm going to do is I'm going to open Offensive Rust process suggestion. I'm gonna just open this folder, see if the pathing for cargo does any better. Go over to our source main.rs. Okay, Rust Analyzer, it's doing its thing. Okay. Now, the reason this didn't work, and if we ran it from PowerShell or something like that, we would see this pretty easily. Is that the default source code that was provided by Trickster Zero is hard coding a process ID. That's no good. We need to start a process and grab its process ID. That should be easy enough if we can kind of infer the Windows API based on what we know about the Nim version of this. Come on. Okay, PowerShell's being weird. While it's trying to sort itself out, let's go back over to our Rust source code and see what we can do. So let's ignore the shellcode for a moment. Our problem is that we're opening this process. The process is hard-coded to this process ID. That's no bueno. We need to actually make a process. So it's probably going to be something like let mute p equal kernel 32. Oh, you're not going to autocomplete for me. Create process, I suspect, is what it's going to look like. And let's take a look at the Nim version of this to see if we can sort of copy pasta our way to an understanding what we need. Of course, all the shellcode's in here, which is super handy for us. Can I collapse that? Not really. Okay, but see how it has, yeah, here we go. Open process. Okay, here we go. So start process is the first thing that we really need to do. Now, interestingly, start process is not part of kernel 32. It is part of the osproc library. That's really what this thing is doing in here. And it returns a process object, which we can get the process ID out of. That's really what we're doing. So to simulate the same thing, we're going to have to use a little bit of Rust standard library, I think, let's see. That's documentation. I want std. There we go. So we're going to do OS. And then std process. Yeah. Here we go. Actually, yes, we do want to do it this way. Process. std process. There we go. Use standard process command. It's going to look like this. So we'll use std process command, just like this, actually. Let's get that in our Rust source. What are you yelling at me about? Oh, it's unused. Yeah, well, give me a second. It will be. The shellcode's all the way up at the top. And part of the reason for that is because all the stuff we're doing here is in unsafe mode. because we're basically using C calls, which can't be guaranteed safe. So this is a Rust thing, right? What we're basically saying is we cannot guarantee the memory safety of this code, so we're going to put it in this unsafe block so that the compiler does not yell at us. So instead of this, we're going to do command new, except yeah, I suppose that should be fine. Even though it's all command, it's not really for console. New, let's try notepad.exe just to make it a 1-for-1. Good. And we don't actually care about the I want the command struct. And we have get program. No. User ID. See if there's any other process stuff, like standard OS process. Yeah. Nope. Same deal. Okay, that's its own process. That's unhelpful. Hmm. Runner exit a child process. Child. Oh, okay. So this actually might work out. Although process struct child. This doesn't appear. All right, so new returns a command struct, and oh, there we go. It has an ID function. There it is. That's how we'll do that. So we're in good shape. So we need we don't even care about anything else, right? Basically, what we're gonna do is, and what type is PID? U32. Which presumably we're going to have to pass as a U64, which is fine. That's easy enough. .id. And then right here, we'll pass PID as U64. Yeah? I think, yeah. Okay, so let's try to compile that and see if we run into any problems. Let's rm rustinterpreter.zip and let's cargo build again. Ooh, okay, we did get a problem. Expected U32, found U64. Oh, it does take a 32-bit. So I don't even have to I don't have to cast it. I was over guessing. Method not found in command. And yet, can you help spread awareness about breast cancer? I have no problem with the cause, although don't really know what you want me to say about it. Okay. Pretty poor as cool as that is, pretty poor cricket to come in here to just advertise your thing. Oh no, that's only inside of process. Interesting. So the methods inside of this are returns the path to the program that was given. That's a string. That's no good. Oh, here we go. This is what we want. We want spawn. Because what spawn will do is give us a result child. And the child, yeah, the child has the ID. That's what we want to do. So dot spawn dot ID. Uh, and we'll do dot expect, because one of the things that is a little bit different about Nim and Rust is that Rust is safer in a bunch of ways, and one of the ways is this concept of a result. So the result type can be either the type that it's supposed to be or an error. And you have to do some sort of checking. There are lots of different ways to kind of unwrap that. Literally, unwrap is one of the methods, but to unwrap a result to determine whether you actually got the type you were looking for or you got an error. In this case, we're going to play it a little fast and loose. There is an expect method that you can use to kind of shortcut this and have a kind of built-in panic, which is what we're doing here. After this, what we have, so if we look at the way this is piped, so new creates a command, spawn creates a result that should contain a child but may contain an error, and expect will kind of handle the error side of things. After which, we should have an ID available to us, or a child available to us that we can then get the ID on. This is getting really long, so the way that I like to write this is I like to indent this. .id. There we go. And that's not yelling at us anymore. So I think we're solid. Let's try to compile that one more time. That built. Okay. So Sure did. Great. So we'll CP Rust interpreter. We'll zip that up. And move that over. Little copy pasta. We'll get that over to our Flare machine. Delete the old sample. And hey, did our PowerShell ever wake up? Oh, it did. Look at that. Okay. So let's go ahead and extract Rust interpreter. Still not getting caught by this defender. Hey, notepad fired off, and we got ourselves an interpreter session. Look at that. That's cool. So honestly, Rust isn't so bad for this kind of work. All things considered, I mean, I really like Rust as a language, and obviously this looks a little crazy. But honestly, let's take a look at what's making this crazy. What's making it crazy is the Windows API, right? All this stuff that we have to pass to the Windows API. If we look at the Nim sample, all that stuff is in there too. That's the entropy. That's the part that makes it hard to read, is the stuff that we're doing for the Windows API. Everything else is kind of just boilerplate. Now, this is one of the simpler examples, but it's honestly not that bad. As a matter of fact, what's wild is I didn't have to write a main function. No, wait, yes, I did. I'm lying. Of course I did. I was like, where's the main? No, it was just up at the top of the code. So far above the shellcode, I forgot it existed. But yeah, I mean, honestly, not that bad. And technically less verbose than the Nim, all things considered. Now, what are your trade-offs? It is bigger, and I have a suspicion. Let's take this same shellcode and see if the Nim sample gets detected straight away as well. We'll do that over here. And I seem to recall that it did, but oh, we already did that. Cool, cool, cool. Yes, so I need to go up to my offensive Nim and cd bin source. There we go. And go to, right. This is, look how much less ceremony there is with the Nim repo. You just have a bunch of the Nim source code files. There's no individual folders for each one. There's no cargo for each one. Now, you technically can write Rust this way, but instead of using cargo to do all the building that we just did, you'd have to use Rust C, the Rust compiler, and you'd have to pass it all these other flags. It's a little bit more annoying to do it, especially when you're cross-compiling from Linux over to Windows. You can do it, and as a matter of fact, for Hack Summer, I built all of the binaries that I needed in Rust, and I did it using Rust C for reasons like I didn't want to make individual folders for each one. So you can do it that way, but cargo is kind of the blessed path for doing that. Okay, so we're gonna go ahead and nim c d ming w for compiling to Windows, and that would be the shellcode bin. Not -c, just C for compile. Uh-oh. I think I made a mistake when I copied over the shellcode. I did. We're also gonna, actually, now I remember this. We have to clean this up just a little bit. we're going to get rid of this when defined stuff. Hey, Husky. Congratulations on your video today. And thank you so much for the blue Jupiter love. Ain't no donut here. This is Rust. Well, actually, this is Nim at the moment, but we just were working on Rust. And take a look. Look at this. This is not that bad. This is the entirety of the process injection code for Rust. I thought it was going to be way, way, way worse. Totally fine. Now, it clocks in at 14 megabytes as opposed to 600 kilobytes for the Nim sample. But, oh yeah, fair enough. No, this is the raw. This is the sushi grade interpreter shellcode that we're just using as a test here. Yeah, it's a chonker. When Al and I were talking about this, we surmised that one of the reasons why it evades some detections is because it's so dang big. Okay, so I think I got this right. Let's try rebuilding this. Still? On line 13,415. Oh, yeah. I duplicated the... Much better. Cool. And then we're going to mv the shellcode bin.exe to nimterpreter.exe. And then we'll cp nimterpreter to downloads. And do I get no detections? So that's interesting that the Nim binary doesn't get detected the way that the Rust did, even right off the bat. That's really interesting. And we know it works, right? So this is kind of point for point. And let's just confirm that one more time. I'm going to move the cp rustinterpreter.exe to WinHome downloads. And what we should see is my defender yell at me. Yep. So very interesting. There's something about the Rust binary that is causing Defender to pick it up and that the Nim binary is not. Now, that being said, we've done extra testing, and what we found is that like the Cobalt Strike shellcode by default does get detected right off the bat. And we have to do extra kinds of encoding to make that get past. So what I want to try with the Rust is I want to try the same trick that we tried before. So we're going to take this shellcode, right? And, oh, nope, that's in Nim. We're going to take this shellcode. It's the same shellcode. I could have copied it from here too. But instead of all of this, this is stupid. Why am I doing this? Okay, we're going to cut that. And we're going to do a little Vim magic here. So, yeah, let's do it in Vim. And I'm mainly just doing this in my Kali machine rather than Windows because, interestingly, the clipboard integration that I have between my Kali virtual machine and my Windows system is better than the clipboard integration I have between WSL and the Windows host. So let's just Vim this up. We'll paste in the shellcode. Obviously, it's a hot mess. What we're going to do is we're going to get rid of some spaces. Oh, God. It's got one of those. in there. Thanks, Windows. Thanks so much for that. Nope. Good. We're going to get rid of those Windows line breaks. Good. Then we're going to remove any spaces. Awesome. So it's nice and clean is the plan. Okay. So now we're going to treat this like text. And to do that, we're going to just pipe this whole buffer to base 64. And we're going to yank that, coming back over to our Rust code. We are going to change this out a little bit. We're going to say let sc equal, and it's going to be a little bit interesting, string from, and then we're going to paste all this in. Stupid, yes, but works. Now, this string, ginormous though it is now a proper Rust string, which means we can do some cool stuff with it. Now what we need to do is we need to base 64 decode the thing. So basically we're repeating what we did with an interpreter test. So we have to base 64 decode it. That gives us a string with each, and then comma separated 0x formatted bytes, right? Then we have to split it on the comma, which we can do. Then we're going to have to extract the string, the hex representation, and turn it into the actual byte, basically, is what we're trying to do. So to do that, we're going to have to learn a little bit about how Rust plays with these things. So the first thing we need to learn is about base 64. And I'm pretty sure there's just like a B64. No? Is it base 64? Let's check crates.io to see if there's a base 64 library. All-time 49 million downloads. Yeah, I think this is it. So what we'll do, the way that you add dependencies to a Rust project is you kind of take this right here and we'll move over to our cargo.toml and we'll add base 64 to our dependencies. The next time we go to build this thing, cargo will be like, oh, hey, you have dependency, a new dependency that you don't have installed. Let me go grab that for you. And it'll go download that. Kind of the same way that pip or npm or really any other modern dependency management system works. Pretty nice, honestly. And actually, because of that kind of automated part, if you recall, Nim doesn't do that. Nim, if you don't have the package already installed through Nimble, it'll just fail the build. That's not the best, I feel like, behavior. I think they could maybe work on that a little bit, but it's still pretty new. Rust has had a bit of a head start on getting its dependency management ducks in a row, but it was also designed from the get-go to feel like a modern high-level programming language from the tooling standpoint. So that's one of the reasons why this works a little bit better. Okay, so we've got base 64, and so we have to put that in our dependencies. Extern create brag base 64. And then this is going to be the fun part. And Husky, if you're still there, you'll really like this. We're going to start chaining methods, and this is the Rust way. And this is the kind of stuff that you do in Rust that makes me like the language so much, because it becomes very clear what you're doing with your data, transforming it from point to point. So basically we're going to do sc dot, notice that it has as bytes already, so hang on to your socks there. But actually, what we want is, sorry, wrong spot. Yeah, use base64 decode. That's actually all I need from the library, so I'm gonna just go get that. I don't need encode, so I'm just gonna use base64 decode. And then decode should be available to me. Yep. SC. And notice that it returns, oh, are you kidding me? So decodes returns a result containing a vec of bytes. The problem is that I don't want a vec of, a vec is like a list or an array. I don't want that. I want actually I want string from UTF-8. Yeah. So UTF-8 takes in a vec of U8 and gives us a string. So actually what we're going to do is from UTF-8 base64.decode sc.unwrap. And we're going to say let decoded equals unwrap. And notice that Rust Analyzer is giving me my nice little type hinting here. It's telling me that it's a string. So what we're seeing here is we're pulling it from a sequence of bytes. And then the unwrap in the interior here is from the base64.decode. And then the exterior one here is for the actual conversion from UTF, from bytes to the string. Now, why do we want to do that? We want to do that because we actually are going to impact this a little bit. Unwrap. And then what we have to do from here is dot split. Because what we're going to do is split on the comma. Right now we have a split. And a split is a really interesting type. It's an iterator. So then we can map. And now all we have to do... Hey, Curious Jack, thank you so much for the raid. Appreciate the return favor. Yeah, check out Curious Jack. He is a legitimate professional. I only play one on TV. So what do we have here? We have a split object. And let's go look up split. This is, again, where the... Hey, Flangvik. Let's go check out split. So a split allows us to get an iterator, basically. It's an iterator. You can see that it implements iterator. So what are iterators? Iterators are, think of them almost like generators in Python. They are not yet sequences or arrays. You can't index them. However, you can do iterative operations to them. And that's where like map and other things come into play with iterators. Really, really handy. You can convert back and forth between iterators and vectors or whatever. One called Pat, thank you so much for the follow. But we want this thing to be an iterator right now because what we need to do is we need to map. And what we need to do is we need to map a function that takes a string that looks like 0x whatever and gives us back the resultant U8 value. Um, so let's look at U8 just to see if there's like a from the primitive type. Yeah. From string radix. Oh, yes, 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 yes. This will do it. Converts a string slice in a given base to an integer. This is it. So what we'll do is we'll call from string radix on the string slice that we're getting here, right? And then we're going to use a radix of 16, right? And that should give us our U8. Let's see how that goes. So we're going to do map. And map is going to take a procedure because it's actually called a closure in function. So what do we have right now? We have a split, and inside of the split are string references. That's exactly what we want. So we're going to map to each, we'll call it S for string, right? We're going to map what was it, from stir radix, right? And we're going to give it the S, and then we're going to give it the radix of 16, which then gives us unwrap. What are you yelling at me about? Oh, it's got collect. So what we end up with is actually a vec of U8. Exactly what we were building before here, believe it or not. Oh. What did I forget to do? I forgot the internal unwrap. There we go. So, oh, it's just decode, not base64.decode. There it is. Okay, so this is the obfuscation that we played with before. We're just base64 encoding the bytes, right? And then we are splitting on the comma, which gives us a string of like the 0x's, right? Then we are mapping each of that against a function that takes a string representation of hex code, right? And turns it into the integer that we want for the byte. Then we don't even have to do this let test. Well, maybe we do. Let's comment that out, and then let's try to send it decoded here. And then where are we sending this thing? I'm looking for where we actually create the remote thread, or we inject the write process memory. Oh, there we go. Decoded. That means I think we're good to go here. The stuff that we're getting yelled at about is about the fact that Rust Analyzer can't see the kernel 32 stuff. But we're not getting yelled at for anything else. So let's go ahead and try to compile this and see what happens. It built. Now, moment of truth. Let's see if Defender makes any noises. Nope. Incredible. So this very, very like stone stupid obfuscation method actually gets past Windows Defender. Stay tuned, Dex. Thank you so much for the follow. And it works like a charm. Now, it is gigantic. Now we can see both. Now that we have both of these successfully living in my downloads folder without getting screamed at. Look at this. So the Rust binary, 15 megabytes. And then doesn't it detect it once it's decoded in memory? Let's find out, Sar. Also good to see it. The Nim one doesn't. So let's move this over to Flare. Kill this. Yeah. Copy and replace. Is this staged or stageless? Good question. This is stageless. Yeah, the here you go. This is the MSF Venom line right here. Okay, so let me. Okay, let's run this job again. Okay, so we're listening once more on our Kali machine, and then over here, let's fire up Burst Interpreter one more time. Ooh, this might be why it didn't. So Flying Vic, we got this thing to load without detection before. Now we're just obfuscating it so that Defender, like a newer version of Defender, doesn't catch it. So far we're doing okay. Now we haven't run everything crazy with it, but it maintains a pretty constant session. So let's see. Called result unwrap on an error value. Ooh, invalid byte. Cloud submission enabled on Defender by chance? Hey, Curious Jack, great question. This machine is completely offline. So even if cloud submission was enabled, yeah, even if cloud submission was enabled, it's this sample is not gonna catch it. It's a great question though. I do want to check it against virus total though, just to see what catches it. Virus total's like, are you seriously giving me a 15 megabyte file? Ooh. Ooh. Ouch. So, what do you think? What do y'all think? Rust. Hey, Lasso. Isn't it morning for you? Okay, sorry. I think I need you to explain a little bit more what you mean by heuristical engine. Because, like, there's like, as I understand the EDR situation, you basically have signatures, partial signatures, like component signatures, and then you have behavioral stuff, which requires API hooking, and then that or event monitoring, and that is pretty rarefied. Like Defender gets to do it a lot because it's already hooked into if it runs at a sandbox. So right off the bat, Windows Defender is not running in a sandbox for us. And it runs through the base 64 and they have a memory pattern that's the same as the unencoded payload. That's still to me that's still a signature. When I hear heuristic, and maybe I'm not using the term correctly, but when I hear a heuristic analysis, it's about behavioral patterns, right, that are independent of static signatures. Um, where you have like a sequence of events that triggers the alert as opposed to anything that comes from static analysis. Um, because at the end of the day, uh, whether it's the result of the base 64 encoding or not, it's still a signature, right? So, and I could be using the term wrong, but in my experience, like it's like yeah, if it's analyzed, it depends on like the thing with EDR, and I think this is like a common misconception. We were toying with this idea, and maybe somebody on here knows, but I do not believe that most EDR, and certainly not Defender, on the system will sandbox an executable and attempt execution preemptively. You know what I mean? To like do essentially a dynamic analysis of something. It doesn't do that. First of all, if it can't sandbox it, that would be super dangerous. It's like, let me just look down the barrel of this gun to see if it's loaded. Like I don't think it's doing that. Um and also that would be an amazing performance hit, right? If you're basically pre-executing every executable that you see going in. I don't think that's what Defender's really doing. Now you can set up Defender. Uh, so Jack, I encoded it with base 64. Let's go back to the shellcode. So this is just like straight up Meterpreter 64, right? Stageless. What we did with the shellcode was we took the literal like 0x chunk of text and we base 64 encoded all of that. So that's what we have here. To get it back out, then what we're doing is we are, God, this thing is so large. We are base 64 decoding it, which gives us um, a single string. Then we are splitting it on a comma, which gives us individual string slices, right? And then we are mapping that against a function from string radix, which takes a string representation of a hex and turns it into the integer we want. And then we're collecting it. Now, the problem we seem to be having is that we have a bad byte somewhere, but not in the classic bad byte sense. Invalid byte 7610 on line 17,812. Right. Oh, interesting. So this is what's actually causing the problem. Uh, I think I know why. It's because this thing needs to be no line breaks. I just want to search. Can I search just? Yep, find in selection. There we go. There seem to be a lot of null bytes and patterns in that payload. Can you try and compress it with zlib? And yes, Zara, I can do that. I want to wait on doing that because I want to see if we can actually get this to fire off first. One call, Pat. If you run the Defender ATP, then yes, it's sandboxes, but you're right, it's a killer on the CPU. Oh, Defender ATP, right. And that's, let's clarify, that's a separate product, right, than straight up Defender. Let's check out base 64. I think, let's see, do we have the option in the base 64 library? Well, we need to get it to run first, Czar. Then it's already bypassed. Let's see. What am I looking for? I'm looking for, we had base 64 decode. I want to see docs. Show me decode. Okay. So we're failing on the base 64 decode, which is... Oh, wait a minute. Wait, well, no. I was thinking... Never mind. I forgot a step. I was thinking, oh, of course it's not going to decode because we're trying to turn a string into something from raw hex, but that's not true. We're starting from a string. Oh, wait a minute. Actually, yeah, we are. This is a little bit reversed, which is the problem, I think. Because this is a string, right? SC is a string. So what we really want to do is, I don't have to do this part, right? I just have to do decode, unwrap, which gives us oh no, I do want to do that. So when I'm this is where Rust gets interesting. We have a vec of 8-bit integers, right? That base 64 decode is giving us. But if we want, because the commas are in there, right? That's why we want it to be a string first. That gives us a string. Then we... Does that still work? No. I need the unwrap in there. Ooh. Oh, hold on a second. We had a second unwrap, didn't we? No, it's right there. What's happening? Like, why did this all of a sudden start erroring on this? No method named unwrap for such string in the current scope. Oh, really? Split returns a vec. Or no, actually, it doesn't. It returns neither zar. It returns a split, which is an iterator. String from is not satisfied. Decode gives us evacuate. Oh, interesting. Um, the map function. I'm glad you asked about that. So map is, think of it as a for loop in one move. Think like we have an array or a list or whatever it is, and map is in Python too, right? Super super handy. Um, as a matter of fact, I know that you're a Python guy, so let's do a quick Python demonstration of a map real quick. This is the programming evening, so we get to talk about just like code in detail. All right, so let's say I'm gonna start with a list comprehension, which by itself is actually a map of sorts. So or let's just do a range, right? So we'll do list range 100. Okay, I should have just saved that to a variable ends. Okay, so I have myself this list of ends, and let's say I wanted to square every single one of them. I have three basic ways that I could do it. Here's the most explicit way, right? I could say squared ends equals an empty list, and then for n in ends, squared ends equals or squared ends dot append, right? N times n. Yeah, and then if we ask for squared ends, now we have those squared. There are a couple of other ways to do this. This is the, as I said, this is the most explicit. It takes 3 steps. Python has this really cool capability called a list comprehension. And this is very, I think a couple of other languages have something like this. In fact, I know for sure Haskell does, but it's very Python-y. And what you do is you create your list, and then inside the list, you basically say n times n for n in ends. And what that does is produces a new list based on this operation. Right? So it produces the same thing. So that's the list comprehension way of doing an iteration. That's that way. Now, the third way is map. And map, what it does is it's designed to take a function and apply it to every single element in a sequence. So with map in Python, we take 2 things. A function, you could do a named function, or you do a lambda, which is Python's anonymous function or one-off function, right? So I could do like def square, just quickly create a square function and return n times n. And then what I could do is map square onto ends. And what that produces is a map object, which is not super helpful. But the reason it does that is because it's a generator. It could get super big, right? It doesn't know what the function has done, really. It could be a lot of data. So rather than give you everything all at once, it saves it in this generator. And I can manually call next on that if I saved it in something. Or I can, and I'll do this often, is I'll quickly convert it to a list. And I get the same result again. So that's what map does. If I didn't want to make a named function, because it's passing, by the way, it is implicitly passing each element to this function, calling it with that element in turn. If I want it to be a little bit more explicit, I could create a lambda function and say n times n. There's the same implementation, right? Same deal. So kind of 3 ways of doing the same thing, but that's all that map is doing. It is absolutely reminiscent of LINQ. Yeah. LINQ is a functional programming language. It's funny too, because like you do F sharp and then you do link, and it's like, oh, this is just F sharp, but buried in C sharp. Okay. Yeah, no problem. I'm a functional programming dork. I love talking about stuff like that. As a matter of fact, it was a toss up today whether we were going to be doing Rust and Nim or we were going to be doing Haskell. I think there would have been an exodus if I had done Haskell, but someday I will convert all of you to the one true language. Oh, are you? That's amazing. Okay, so what's our problem here? So the issue here is the trait bound string from vec8. This isn't a super useful error message if you don't know what Rust is doing. Uh, if you're familiar with C sharp, traits are interfaces. They are, or if you're familiar with Haskell, they're type classes. They're essentially guarantees that structs have that allow you to move from one thing to another or guarantee that they have certain methods. That's what traits are. So there is no trait of from for there's no trait from that allows a conversion from a vec of u8 to a string, which is what we're trying to do with this decode. Um, and that's because it's not string from. I just forgot that it's from UTF-8, and I'm gonna try UTF-8 lossy just in case that solves my problem. Okay, now we've got a decode issue. Expected reference. Oh, really? Okay. Done. Okay. So what is the difference between UTF-8 and UTF-8 lossy? That's worth talking about. Oh, I'm in base 64. I'm not in the standard library. Is it kind of like, I hope it's becoming clear why I like the Rust documentation so much. It's super easy to search and it all looks the same way. But yeah, so here's from UTF-8. Our string requires that it's valid UTF-8. From UTF-8 checks to ensure that bytes are valid UTF-8, then does the conversion. If you are sure that the byte slice is valid UTF-8, you want to incur the overhead of the validity check. There's an unsafe version of this from UTF-8 unchecked. Oh, perfect. That's what we want. We want from UTF-8 unchecked. We're going to do that. It's unsafe, but whatever. So is the rest of our code. So instead of lossy, well, let's talk about what lossy was before we go back. So lossy, including invalid characters. So they're kind of the same thing, but I do want to try unchecked to see if we can just beat the wrap that way. Oh. A new raid. C cubed coming in. Oh, actually. Yeah, it's yelling at me that it's unsafe, so I have to put it inside the unsafe block, which we knew was going to happen. C cubed dev, thank you so much for the raid. Now, technically, this indentation doesn't matter because Rust is not white space sensitive, but I'm white space sensitive, so I'm going to try to fix this. It's going to bother me otherwise. Okay. Yeah? Yeah. Okay. Let's try compiling this and see what we got going on. I forgot I didn't actually have to be in the top level to run cargo build. It's smart enough to figure out where it is. So still no alerts. Let's move that over to Flare. Dang it. The stealth giraffe. I can't see you, but thank you so much for the follow. This is a good old Rust puzzle called result unwrap on an error value, invalid byte. Beardonian, thank you so much for the follow, friend. All right, that didn't matter. So let's go back to just from UTF-8 because that didn't seem to make any difference. And now we have no method name split in enum results. So, right, we have to unwrap that. That's so interesting. Okay, so we have to unwrap it if we're going to do from UTF-8. The problem is that this thing... Let's just do a quick sanity check and make sure that this actually decodes the way that we think it should. Head over to CyberChef. It does. Is there something funny in my logic? So here's our string. We're making a new version of the string that is... So we base64 decoded. That gives us bytes. A vec of bytes. And then we put it all back together with a string. You know what? I'm gonna comment this stuff out for a second. And no, because we know it errors out there. Like it errors out right here. Am I doing something very dumb with the base64 decode? Wait. Decode from string references octets. Return a result containing a vec. Input base64 standard. What kind of configs do we have? new character set and pad. So the default decode I feel like what we need to test out base64 decode by itself to make sure that we're not totally crazy. So we're going to comment out pretty much all of this. And we're going to just say okay. And then we'll say equals decode test dot unwrap. And then we'll print line. This is the debug print line for decoded. Yeah, okay. So we're going to cargo run this, actually. Could not compile process injection thread due to previous error. 2 warnings emitted. Oh, hold on a second. I have to cargo run. Well, let's build it, right? And then... Okay, so that works. Notice that I was able to call the exe from WSL. Now, from UTF-8 dot unwrap again, and then we're going to just print line decoded like so. So now we have a string that theoretically is made of the same stuff. So our logic is fine. The problem is our shellcode. That the B64 encoding is like giving us a headache here. And I have a feeling I know what that's about. Let's go back over into actually cut it. Let's go back over to Kali. I don't think I saved that, did I? Look at that. I have got multiple lines. And again with the spaces. So we're going to get rid of those. We're going to get rid of the Windows line breaks. And we still have multiple lines, right? And I think that's our issue. So what we're going to do from there is we're going to get rid of any new lines. Aha! I think this might have solved the problem for us. Just text stuff. Yep, one big old line. which I can't see the end of. It's too long. It won't show me the end of it. Okay. Now I can see the end of it. Okay, great. And that's one line. That's what you want. All right, so we can get rid of this junk. We'll re-uncomment this. That's all still looking good. Let's recompile. And head over to Flare. Get rid of the old one. Fire up the new one. Crap. Different problem, though. That's nice. Now we're having a problem about an invalid digit. And that's on line 15. So that's actually great news. So split, let's make sure we understand how split should work, just in case I got something wrong there. An iterator over the substrings of this. Oh, no, it is wrong. Oh, no, it's not. No, it's not. Yeah, it does exactly what it's supposed to do. Separated by characters matched by a pattern. Okay, let's do a little bit more creative commenting here. It's a problem. Mismatch types. Expected struct vec string found split dot collect, right? Collect is how we turn that thing into a vec again from an iterator. Great. So now that we have that, we are literally just going to print line decoded, because I want to see what this looks like. Creates a temporary which is 12. Creates a temporary which is freed while still in use. Uh-oh. Temporary value is freed at the end of the statement. Oh. Yeah. we have to do something like this. All right, that looks good. By splitting it up into two parts, we should fix the borrow checker problem. We did. So obviously, we have a problem, which is there are still a bunch of new lines in here. That's what's killing us. Even though we replaced the new lines. And in fact, this is something that I accounted for in the Nim code, and I really should have done it here too. Which is for each of our individual strings, I need to strip a suffix or trim, right? Returns with leading a trailing white space. Yeah, trim is what I want. So what we're going to do to fix that particular problem is, let's kind of back out of all this because we don't need this split up this way anymore. Come on, come on. Good. So it's s.trim that we're going to give to the from stir radix. That's the trick. The trim then gets rid of any of that annoying white space in the string, which will allow the conversion to happen cleanly, I'm hoping. Okay. Can I build release to see if it's any better? I want to see what the release compile size looks like. That's going to take a minute. And see, it says release optimized, and we're in debug. That's much better. I mean, it's still gigantic, but it's 5.8 megs versus the 15 meg unoptimized. So doing a little bit better there. Much, much better. 5 megabytes is tolerable. 15 for something like this just seemed ridiculous. All right, we're still not getting it, unfortunately. Parse int error. So we theoretically we trimmed, but we may need to be a little bit more aggressive. It's possible that new lines aren't considered white space. What about trim end? No. We can try strip suffix. and give it a new line and see if that does better. So strip suffix, if the string ends with it, returns the substring before the substring. Trim end matches. Oh, actually, I like this better. Oh, hey, Handel. Sorry, I was in the zone there. What do I think about today's news? Yeah. So the Twitch breach. I mean, it's deeply unfortunate. We don't know the why. We don't know the how, and I don't want to speculate too much. Um, it sounds like it was kind of a prolonged situation, right? It wasn't like a quick. It wasn't a quick smash and grab. It seemed like the attackers took their time. They got a lot of data. Now, the fact that they were able to exfiltrate that much without getting caught is very concerning to me. That's like the biggest thing. In order to get that much data out, and especially source code, like something went wrong process wise. But the truth is, this isn't the first sensitive place. Like, do we consider Twitch to be more concerning than a bank? Because we know that banks have had breaches before. I think that it's a good reminder for all of us to use the basics in our personal lives as much as our professional, right? Multi-factor authentication everywhere, not just SMS multi-factor, but use an authenticator app or something else like that. Go as hard as possible. Make sure that all of the accounts that are connected to your streaming account, um, including any bank accounts or anything else like that, that if you're an affiliate or partner, you want to make sure that those are protected as well. And if there's any additional monitoring you can set up on those accounts, make sure that you talk to your financial institutions and set that up just to make sure that there's nothing squiffy going on there. Because you never know, right? Um, those are good reminders. I don't know. This one hit close to home, closer to home than a lot of other breaches, of course. It's it's really disconcerting. It once again drives home the point that we're doing all this offensive stuff tonight, and it's fun, and it's really exciting to do this, and it's fun to explore. But the truth is, friends, the blue team needs your help. It really does. My day job is defensive, and it is really hard. And I work in healthcare. Um, we're in trouble. Uh, we do our best, but like we have to be right every time. The bad guys have to be right once. You know, we have to slip up one time, and how are you gonna not slip up one time? So if you are looking to get into this industry, if you aren't already in it, if you're interested in infosec and you want to find something, I have to say, look, blue team is hard. Sometimes it's boring. It doesn't have the glamour of red team. But here's the deal, especially in healthcare, like I wake up every day knowing that the work I do protects patients and caregivers. I go to sleep every night worried about those patients and caregivers, but I know that during the day, like on a good day, I made a difference. I know that I did. And red team, you guys do the same thing. I really respect what you do. Obviously, I'm trying to do a lot of it. I'm trying to bring a lot of the offensive practices in house. That's part of what my job is basically to invent a purple team. But um, every time I see somebody online, it's like, I want to get into pen testing. That's great, but we need so many more defenders. We really do. And we need good defenders. We need people who understand this stuff and understand how to look at network telemetry and see where attacks are taking place, how to look at Windows events and understand malicious activity in Windows event logs. We need all of that stuff, and we need it now. So if you are looking to get into this career and you're enamored with the offensive side, that's great. Pursue your dreams. But may I also consider that there's a lot of exciting work to be done, or may I ask you to consider that there's a lot of exciting work to be done on the defensive side? You may not be as familiar with it, but it's really, really cool. And if you can find the right spot, it can be incredibly fulfilling. You want to start a purple firm? That's the end goal. More power to you, hate handles. Absolutely. It's a hard thing to do. Um, Purple teaming the right way. And even, especially if you're bringing the offensive to a defensive, if you're bringing the offensive skills to a defensive party, um, you're not the person that people want to hear necessarily. um, or maybe you are, because a lot of times with pen tests, part of the objective of pen tests is to unlock budget that the blue team has wanted for a while. Um, but in a proper blue team, another one of the in a proper purple team, another one of the constituents may be the owners of the systems, not just the defenders, which are two different constituencies. And in that particular case, you have a really, really tough uphill battle against operational reality. You don't just have to fight against, this is what you're supposed to do, but like if it's going to make any difference in their operational day to day or make life harder for them, that's a very hard sell. Yeah, it is the only way. It's the only way forward. I mean, the Andrew Thompsons of the world notwithstanding, who believe that imposing cost is the only way forward, which is not a realistic possibility for most organizations. Um, the only way to survive this new reality is for the defensive capabilities of almost every organization to get exponentially better. And that's not going to happen, by the way, with tools. It's not going to happen with a Blinky box. It's not going to happen with any amount of enterprise spend on licensing or products. It's going to happen with spend on personnel and training and ongoing training. There are so many cyber jobs that are going unfulfilled. Why? Because organizations would rather try to find somebody who already has the skills than invest in training people who are willing to learn. The onboarding process that used to exist in a lot of places no longer exists. They expect you to come in as an entry level with a CISSP, a SEC Plus, and an OSCP, and whatever else. It's not realistic. So all of a sudden they're like, well, we can't hire anybody. Why do you think that is? And by the way, the math doesn't even work out because think about all the personnel hours you spend trying to find that unicorn. Like that costs you money. Every day you spend trying to hire somebody who doesn't exist, it costs you money. Instead, if you took that money and onboarded somebody who has a lower, set of resume bullet points, but is willing to learn, you could shape exactly the employee that you want. Sorry. Hate handles, you hit a chord. Being nimble and taking action where gaps are found is the way, not blindly following policy distribution. So much self-preservation, lack of urgency. Yeah, there's a lot of fear. It really depends on the culture. People don't want to get caught out being the person who made the bad, like made the mistake that made things harder or worse. Try trim end matches. At least this one's a slightly different size. Hate handles, I'm glad to hear that you're at a place that you really like. I have to say, I like where I am too. It's a really it's a really nice spot. It's a public institution. What am I doing wrong? Okay, we're gonna have to go back to the old school debug here. So we're gonna. Oh, really? That's cool. Oh, crap. Uh, Thank you, Heath. Incredibly great to see you. I mean, a little redundant, but let's shout out the Cybermeter. Wow, Shad257, me hack. Thank you so much for the follow. Um, Heath, if you're still there, you may not know this, but you were responsible for some of my first certifications and one of the reasons, like one of the original reasons I got into this industry. So thank you for all the work that you've put in, and you were one of the inspirations that got me streaming. So thank you very much. And I'm excited to see my buddy Husky's course material on your platform. Oh, fair enough. I can still send gratitude out into the universe. Oh, there he is. Red Ace. Dangerger. Thank you so much for the follow. Vinuistic. Yeah, it's something else. Jamie, thank you for the follow. All right, so for those of you who uh, are sticking around, what we're doing is we're building out some malware in Rust, actually. And we are kind of obfuscating some interpreter shellcode, and we are getting it to run in Defender. And we're running into a dumb Rust problem. Our shellcode actually works fine. And what we were doing earlier is comparing it to Nim. And we got the Nim sample to run, and actually, we got the Nim sample to run and not get detected by Defender. Um, Pretty excitingly. Gigetto Dev, thank you so much for the follow. Um, so we're trying to reproduce the same thing in Rust just to see what the differences are. And so where we are right now is we are converting our base64 encoded string back into bytes, and we're running into a weird issue that the conversion just isn't playing ball the way that we want. So we're going to kind of test this out a little bit. We're going to do .vec. Yeah, let's comment this out, and we'll try it this way, right? Say let decoded equal string from UTF-8, and basically the same thing, decode sc.unwrap. Pacero, IT career questions, thank you for the follows. And we have to unwrap that too. And from there, we are going to we don't want it to be a string, actually. We want it to be a vec of strings. So to make that happen, what we're going to do is we're going to take this string and we're going to unwrap it. And then we're going to split it on the comma. And then we're going to map the wait a second. Split dot. Nope, that should work. Split dot map, and then we're going to say s dot trim. Why is this not working out for me? Dot split. This unwraps. This becomes a string. Dot split. Oh, there's not a dot there. There we go. S dot trim end matches, and we're going to give it the pattern of a new line. And then collect that. The size for values of type str cannot be non-compilation time. All local variables must have a statically... Oh, because we're in unsafe, right? No, not why. What's the problem here? The size for values of type str cannot be known at compilation time. The trait size is not implemented for str. All local variables must have a statically known size. Unsized locals are gated as unstable feature. I mean, fine though, right? And yeah, we're gonna print decoded. Let's see if that lets us compile. Nope. Doesn't have a size known at compile time. Oh, if I didn't reference it, it was fine. I did a reference when I didn't need one. Now what's the problem? Creates a temporary which is freed. Oh, right. Okay. So this is what our problem was before. And let decoded equal string. So the way that the reason that chaining is such a problem is that the way that the borrows work. Oh, Shat257, you're so welcome. The way that the borrows work is that if we try to do a split and then a map across these, Rust's borrow checker trips because it's no longer memory safe. Now, technically, we're in an unsafe, so that shouldn't matter, but it still does. Okay, right. So by splitting it up, and so now the compiler is like, okay, both of these need to survive. Fine. Then we're able to compile. Oh, they're at the beginning too. So can we... those aren't enabled for Hawken Live. Let's do trim suffix. Actually, let's go back to our Rust documentation. Trim. There's like strip prefix and strip suffix. Trim left matches. Return with all prefixes that match a pattern. All prefixes that match a pattern. Okay, so this is a little bit funny. I think we can just do a replace, though. And actually, now we have to know if it's on a stir. Do I have a replace on stir? Oh, I'm being stupid. That's the way to do this. We'll just do s.replace. And what does that return? It returns a string. as stir. So weirdly, I still actually have to convert it back into a primitive. There are two string types in Rust. There's the primitive string, which is like a naive, uh, essentially array of characters, right? And then there's the string struct, which is a little bit more mature and has other stuff. Oh, you're looking for the hack list? There they be. Okay, let's try that. Shad, thank you so much for noticing. I was wondering when someone was going to comment on that. Wait, what's my problem now? Returns a value referencing data owned by the current function. Oh, you know what? Easy fix for this. Two maps. So the problem is that we can't do a borrow like this, but we can do two maps. So the first map we're going to do is map S and then S dot replace um, and then map S as stir. I'm hoping that solves the problem. Nope. Returns a value referencing data owned by the current function. Oh, hold on a second. Okay, so one of the things you can do to get around an ownership problem is .clone. So we're able to send a copy of it. Come on. Returns value referencing data owned by. Oh, wait, hold on a second. It's the as stir that's a problem. Right? Boo. Okay, let's go back and look at as stir to see if I forgot something dumb. So string as stir extracts a string slice containing the entire string. Right. Hey, little Didi. All right, we'll do this in a couple different stages then, because so we're creating a decoded iter, and this makes it a what? A split, right? No. Okay, we'll make it a vec with a collect. map stir split. I know we're running long, but I really want to get this. But why are there new lines at all? You know what I mean? There shouldn't be any of them in there, but whatever. That's split. Actually, hold on a second. We might decoded. We have a better way to do this. Right? Because replace we can operate on the whole string. So so this is going to be a vec of stir, right? Oh, I need to collect that, right? Yep, there we go. Okay, so now collect, what collect does is it takes this iterator. A split is a kind of iterator, but whatever kind of iterator we have, a collect will turn it back into an array or a vec in Rust language. So hopefully, what's the warning we got here? Creates a temporary which is freed while still in use. So we'll make this a string. And then we'll say, let decode vec. How long have I been in IT? I started my IT career, well, I mean, technically when I was around computers from a very young age. My dad had machines in different stages of disrepair all over the house when I was a really young kid. And to get any of them to work, I had to put them together myself. But I started professionally working in IT in 2008. So, God, what's that, 13 years? And yeah, have been doing it ever since. And I moved into InfoSec properly, I don't know, about 3 years ago, I would say. Okay. That's not giving us any issues, but maybe the compiler will yell at us? Nope, the compiler did not yell at us. So let's run that. Yo, that looks right. So to convert that into our actual code, what do we have? We need to do dot replace dot split. Now the replace is the problem. So we're basically gonna do a little bit of dot unwrap. Oops. So unwrap. We're going to copy this replace down here. And so we're going to basically make the decoded a string. The same way that we did up here. Right? Not that different. Then we're going to say almost the exact same thing. We'll say the let decoded vec, except it's not going to be a vec of string anymore. Now it's going to be a vec of U8, because what we're going to do is decode it. We're going to split it, which we already did here. Then we're going to map the from string radix, and we've already taken care of the new line thing, so we don't need to worry about that anymore. And then we're going to collect it. Let's get rid of this and this. Okay, so we finally have solved the new line problem, we think. Okay, that compiled. Let's move our Rust binary over. And if this one doesn't work, we're going to call it for tonight, friends, because I got stuff to be doing. But fingers crossed. Crap. Well, now it's failing at a different place, but I think that's because we changed some lines. So we're still getting a parseInt error with an invalid digit. I'll continue to work on this, but I think we're close. But the big takeaway is that neither one of these got detected by Defender, even when we weren't trying to do the obfuscation. So really cool stuff. I think that Rust has a lot of promise for a red team language, especially with this Win32 API. I still think Nim is a little bit more ergonomic, but don't count Rust out. I think that there are some advantages to using it, especially when we get into these like really nitty-gritties of dealing with bytes. So I think that's going to do it for tonight. Thank you so much for hanging out. I hope you had a good time. I will be back on Saturday, 10 a.m., doing some blue team stuff. Now, also, I would be remiss if I didn't mention that I will be speaking at ShellCon this Friday at 1 p.m. Pacific, talking about, I'll be using my background as an educator to talk a little bit about what it takes to self-teach yourself skills in tech. So if you're interested in that, check us out, shellcon.io. It's pay what you can, so definitely worth checking out. Until then, let's see if there's anybody else streaming right now. Oh, the Guar is streaming? You know what? That'll be fun for him. We'll give the Guar a quick raid. All right, so friends, until next time, be good to yourselves, be good to each other, and happy hacking.